Hi Bella, this is Mr. Hausman, and we're going to take a look at page 11, another couple of problems with objects on inclined planes. So this one is actually very similar to the one in class, but in case you felt rushed or it was, just before 8 o'clock, pretty early in the morning, let's do another one where we're examining the forces that are on the sliding object, and specifically what we're going to try to do is we're going to try to find the friction force. Now, one thing we know about friction force is that it's against the motion. It's never in the direction you're sliding or you're moving or you're about to move. So let's see if we remember how to do all of the forces on this object. So the first thing we're going to do, and we never change this, is the first force we draw is Fg. Now, we don't actually use Fg directly a lot in problems when they're on inclined planes because, as we know, all of the forces are perpendicular and parallel to the hill. So I'm going to start using color, though, to make sure we're clear on which direction the forces are. So if you turn your paper now, it's a little bit easier to create what we call the force of gravity in the y direction. So here's the center of this koala bear. No, what kind of polar bear? Looks like a koala bear. And we have two forces in the y direction. We have force normal, and we have force gravity y. I think I've made it the correct length so that I can now add in the force of gravity that's parallel to the hill, or we could call it the x direction. So let's see how I did. Yeah, that looks pretty close to parallel to the hill. So now we're going to use green to be the forces that are parallel to the hill. And then up here is a force we can't forget about. It's usually drawn right here along the surface because the bottom of the polar bear's fur and the hill are creating some kinetic friction. Oops, I'm so sorry. I was just off the screen a little bit. I'm going to rotate it back so we can see everything. So here's the polar bear. Let me maybe just clarify. So we've got our FGY, we've got our normal force, they're in the y-axis, our FGX down the hill, and our friction, which is against the motion of the bear. So the hill is 25 degrees, or the incline is 25 degrees. So inside the right triangle, the 25 degrees is up there by the vertex where the bear's center of gravity is. This should be a 90-degree angle if I've drawn it well, if you've drawn it well. So we now know, oops, let's keep the page straight, that the only unknown here is not to find the acceleration, but to find the kinetic friction force. And according to the formula, the friction force is equal to the mu, the coefficient of friction, times the normal. And the coefficient of kinetic friction is provided. It's very small because it's a, wet slide with a polar bear fur on it, not very grippy. And then the normal force, okay, so we can see that in the picture, and we notice that it is equal and opposite to the force of gravity. And gravity being a component of this blue vector, let's remind ourselves that FGY is adjacent to the 25, so we would use cosine of 25, multiplied by the hypotenuse of that right triangle, which is mg. So let's plug that in. Cosine 25 times mg. And we know that these two forces, right, are the same exact magnitude, but the gravity force is negative and the normal force is positive. So we'll just make sure we plug in a positive 9.8 meters per second squared for g. Okay, let's hit the calculator. 0.05 times cosine 25 times the mass. It's a 900 kilogram polar bear. I just looked that up right there at the top of the problem, times 9.8. So there is exactly, let's switch color. There is exactly 399.68, and we can tell that that rounds to 400 newtons of force. Now, you think you're done. That's great. You calculated its magnitude. But because it is up the hill, right, in that direction, we have to decide, is that a positive or negative direction? And that usually is the negative direction. Up the hill is negative. So the standard is up the hill is negative, down the hill is positive when we're dealing with inclined planes. You can technically reverse those, but the consensus among classmates was, oh yeah, let's make down the hill be the positive direction, because that's usually where the acceleration goes. Now let's do the next level 1 problem. This lifeguard is testing out the water slide to see if it's really working right, if there's enough water in it, if it's slippery enough. And we know that this lifeguard named Link is on a 35-degree slope, which is a little bit steeper than the bear. And Link has a mass of 65 kilograms. We actually even have a mu value. So you might be thinking, oh, this is all the same information as the bear problem, except now we're gonna find the acceleration. So that's a little more involved. So let's see how good your free body diagram is. So let's put our force of gravity straight down. So that's mg, right? That's how you find the force of gravity. The y forces, let's put our ruler so that the 90 is right on the hill, the incline. Here's my y, force gravity y, here's my normal. And I'm trying to make those equal and opposite, force gravity y. But let's double check to make sure I did get a pretty good, yeah. So I think I went a little too far on that one. And I'm pretty sure, yeah, let's fix that. There we go. Here we have an FGX, and we have an FGY. Now I can put the arrowhead on it, okay? There's a little tail. I went a little too far. So we've got a pretty good setup so far. With one more force, we need to put in the friction force. You don't have to do this with a protractor, but when you're being precise like this, it makes you kind of take a little more care, and it makes you pay attention to those forces more. Okay, while we are about to do an accelerated motion problem, let's still make a glossary of all the forces we know, right? We've got this hypotenuse, which is mg. We've got FGX, which is in a triangle with a 35-degree angle, sine of 35 times the hypotenuse, which is mg. We've got an FGY. We could use these in future formulas. That's going to be cosine of 35 times mg. The normal force is equal to FGY, but it is, of course, positive. So we've got a positive FGY, positive Fn and negative FGY. And then our friction force, that's kinetic friction, so we would need to know the mu kinetic, and we'd have to multiply it by the normal force. So those are all the relationships that we know either by trigonometry or we know by formulas. Okay, so let's begin now. Let's use blue. So here's what I'm thinking. We learned that all of the y forces are equal and opposite. So the acceleration can't be that way. In fact, I hope it's obvious that the acceleration must be down the slide. So we really only have to examine the sum of the forces in the x direction, which is parallel to the slide, and set that equal to mass times the acceleration in the x direction. Newton's second law says that the sum of the forces must be in the same direction as the acceleration. So if we're accelerating down the hill, it also tells us that our FGX probably is bigger than our kinetic friction force, but I think we have to examine that. We have to put those in. Now, since they are x forces, we're going to go back to the color green, and the two forces we're adding are FGX plus kinetic friction equals the mass times the acceleration, and we don't know the acceleration, right? So there's our unknown. We're going to just focus on that, but we need to do some substitution. FGX is sine of 35 times mg. I bet you knew we were going to do that next. And then the friction force is mu times Fn, but Fn is equal to FGY, but positive, so it's really equal to cosine of 35 mg. So all of this is just the normal force, and then times the mu. And in this case, they don't add up to 0, right? There is a mass, and there is an acceleration in the x direction. Now, you might be a little less comfortable plugging in that many variables, right? Because we actually know the mass, we know the g, we know sine 35. We could do calculations, But look what happens because it's a variable of mass is in the first term, it's in the second term, and it's in the third term. The masses actually drop out. The mass of the person on the slide has no effect on the acceleration at all. And so now we can start plugging in actual numbers if you are comfortable with that. Let's do sine of 35 times the g, 9.8. Now that's down the hill, 5.62. And its units are meters per second squared because that's the unit for acceleration. Now if down the hill is positive, that means when we calculate our friction force, it's going to have to be negative. So the mu value is 0.05, I see that right above, times cosine 35 times g, 9.8. And one way or another, and it will not come out naturally negative, but you have to make it negative. So we're going to make it negative 0.401 meters per second squared. Remember the m's canceled out? So we're really going right to the acceleration. And so we are, it's quite simple, we're subtracting, adding a negative means subtracting, 0.401 from 5.62. Let's type that in, 5.62 minus 0.401, and you get an acceleration in the x direction of positive 5.2 meters per second squared. So it all had to do with finding all of the forces in the free body diagram, step one. Step two, using the x direction, right? All of the important forces that cause the acceleration were in the x. We did use the fact that FGY and force normal were equal and opposite, but we really just used that so that we could plug in the normal force right there. So we've got two example problems. Your task is to do 3 or 4. I'll give you some kind of, maybe you want to catch up, 3 or 4 problems on page 12 and 13. If you start to notice they're going pretty easily, do a 4th. But we're going to do 3 out of 4. Now, the homework assignment says you can do level 1 and 2 or level 3. Level 3 is in a supplemental page, and you don't have it right now, but I'd be happy to give it to you. But I'd be really happy if, for catch-up's sake, you were able to do basically level 1 was page 11. You already have those done. And then you focus in on level 2 problems. Page 12 and 13, pick any 3 out of the 4. You'll find the answers right in the assignment for inclined planes.